Okay, previously we stopped at BCC structure. We give you A equal to 4R divided by square root of 3. Okay, capital R is the radius of the sphere. It depends on different element, have different R value, right? But if you can do calculation, 4 divided by square root of 3 is 0.68, if not mistaken, right? Okay, then another equation is APF, packing factor, atomic packing factor, give you volume of the sphere divided by volume of the cube. Okay, number of sphere. This one is number of sphere. So you know that for BCC, you can fit in 2 sphere. So 2 multiplied by the volume of the sphere, or n multiplied by the sphere. Sphere is 4/3 pi r cube. Okay, you arrive at 0.68 APF. Sorry, 0.68 is the APF. 4/square root of 3. How many? 1 point something, is it? 4 point something. Okay. So, but remember this one. This will help you a bit. Okay. So today we look into another member, also cubic system. We call it FCC. We will do the same approach. If you understand BCC, we'll apply the same approach. FCC is basically you have one sphere at each of the plane face. So one cube, you have 6 faces, right? 6 faces, 8 corner. So one corner you have 1/8 sphere. 1/8 sphere. So 4 corner at the top you get half sphere. 4 sphere at the corner you get another half. So you get 8 corners you get 1 sphere. Then in the middle we don't have nothing. For FCC you don't have nothing because you are packing sphere at the surface. So we have half sphere. Half sphere for 6 faces, you have 3 sphere. So 3 sphere, but 8 corners, you have 4 sphere. Okay, so if you group this one, you get 4 sphere, or 4 round sphere for that. So you can able to calculate APF later with the same formula. Number of sphere multiplied by the volume of sphere divided by number of the cube, volume of the cube. So we want to derive the equation of A equal to something R for FCC. Okay. Previously for BCC we do diagonal to diagonal, but for FCC a bit different. FCC we look at the face. So we have 3 presentation diagram: atomic site unit cell, hard sphere, and isolated unit cell. Usually we'll be using this one, atomic site sphere or reduced sphere presentation. This is how they look like under microscope. This one will look like when you cut the things into cube. We call it isolated means you cut and then you take out and studies it. Okay. Okay. So this is just for your revision. Later we will prove that FCC equal to 0.74. Okay, so this one you should able to prove. Okay, so this one we already know that FCC equal to 4 atoms or 4 sphere. Right, there's an equation. You should able to calculate. So 8 multiplied by 1/8 at each corner plus 6 half atoms, you get 4. 4. Okay. Now for BCC, you across the 2 corners. So BCC 2 corners. FCC, because it's a face centered, you are using the face here to here. So don't confuse between the two. BCC, because you have atoms at the center, you cross the center. Okay, but FCC, you are focusing on the face. So your diagonal trigonometry calculation is on the face. So that's what you see on the here. Okay, on the screen here, you should able to tell how to calculate this purple color line here. You should able to calculate square root of 2 by using trigonometries. How? Trigonometry. What is the side? A. Right? What is this? This will be, let's say I put an x squared equal to a squared plus a squared. This is by using the trigonometry. C squared equal to a squared plus b squared. So equal to 2a squared square root. So it become a. Okay, you should be able to understand how to get square root of a. This diagram is important when you solve chapter 3 question. You should be able to draw this diagram. Okay, you don't need to draw the 3D one, as long as you draw the sphere. As long as you're able to draw circle like that. Okay. Then you should be able to understand how we get 4 capital R. Radius, 2 radius, 1 radius. Total, you have 4 radius. Okay. Equal these two. 4R equal to square root 2R. 4R equal to square root 2A. So we want to always find A equal to something, right? A equal to 4R square root of 2. So don't confuse between the BCC and FCC. BCC is square root of 3. FCC is square root of 2. Okay. So this is for FCC. We need this formula to calculate for complex problems. Make sense? Okay. So if you do calculation, you can do AFP equal to 0.74. How to get 0.74 without substituting value? A, P, F equal to number of sphere multiplied by volume of sphere divided by volume of the cube. So volume of cube equal to A cube. And how many atoms for FCC? 4 multiply 4 over 3 pi r cube. What is A? A is what for FCC? A equal 4 square root 2 r. You can put on the top if you want. So you have 16 over 6 pi r cube. This one you get 4 square root of 2 r and cube it. Okay. So here you can do simple calculation. You pull the r to get out. Cancel. You press calculator. The answer will be 0.74 something. This one come out one time in test 1 to prove APF equal to 0.74. This is the expected answer. Okay, so if the question asks you to prove, you need to draw this diagram. Give me what is the side pi r pi the side equal to square root 2a. Same with 4r. Then write this equation. Square root 2a equal to 4r. Arrive at this equation. A equal to 4r divided by square root of 2. And here, then give me APF equation. APF equal to number of sphere multiplied by the volume of sphere divided by volume of the cube. Put in the equation, press calculator, you get 0.4 something. Okay, 0.4 something. Okay, remember the members for FCC, aluminium, copper, lead, nickel, iron. Remember 3 members from here. Yeah, we move on to FCC, HCP. HCP is a hexagonal cross-spec structure. Bottom, you have 6 at the corner, 1 at the middle. On the top also same, you have 6 at the corner, 1 in the middle. Then in the middle, between the top and bottom plate, you have another 3 at the middle. Okay, another 3 at the middle. So this is how you draw if HCP. Okay. So very high chances this will come out in your test 1 or final exam. If I don't ask you this one will come out in final exam. So a few parameter you need to take care. See this one as 3 parallelogram. If you break this one into parallelogram, it's repeated 3 times. 3 times. So this become 1, then this become another 1, this become another 1. Okay, it's actually it's a symmetry plane. You multiply 3. So you only need to analyze 1 cube only, one cube. Okay, which is this 4 molecule or sphere with parameter A and C. A is side or lattice length, and C is the height of the cubic. Okay, so this is aggregated presentation. You will see something like this. So you have 1, 2, 3, 4, 5, 6 with 1 at the middle, at the top. So bottom also have. So this one at the bottom also repeated. Middle you mix 3 at the middle. Like this one. These 3 at the middle. Okay. So 7 at the top, 3, then another 7. You form a layer. Repeat this pattern for the rest. Okay. So this is called HCP. Okay. So just now we mentioned the A parameter, C parameter, and we have the labeling. We have the labeling accordingly. So as you can see here, we have ABC presentation. Again, atomic site, hard sphere, and isolated unit cell. Isolated unit cell usually we use for analysis. But it's sufficient if you draw this one and you add in the parameter from the isolated cell. Okay. Okay. So matter do not crystallize into HCP as shown because APF is too low. The atomic packing factor is too low. Okay. Okay. So for HCP and FCC, HCP is this one and FCC, each atom surrounded by 12 other atoms. Thus, both structure have coordinate number of 12. How you find 12? Yeah, how you find 12? This is half. This is another half. Okay. You try to imagine, let's say you are this FCC atom. This is half, right? So this atom surrounded by the top four atoms. Okay, maybe I'll show you the FCC. Okay, this one. If you focus on this atom, this sphere, you have, this is 1/8, right? So actually on the top you have 4 here also 4. Let me show you we want to show that the coordinate number is 12, this one. Coordinate number means the sphere is contact with 12 atoms. So if you put at this one, you repeat another cube, you will get this atom alone have contact of 4, plus 4 and 4. So contact is 12. You can imagine, right? If you are this atom, you have 4 on your top, 4 on your below you. So you have another 4 surrounding you. So you have 12. So the 12 actually is how many contact you have if you are that atoms inside FCC, sorry. Okay. And can you guess what is the coordinate number for BCC? If you are BCC, if you are this red dot, how many atoms you contact? 8. Can you imagine? If you are the center, how many you contact? 8. 4 at the top, 4 at the bottom. It's like you Chinese New Year come already, you have lots of Mandarin or this orange, you go and arrange lah. Then you can imagine, right? Okay. Okay, the next is okay. Now this is how you calculate the packing number. So atom at location mark 1 contribute to 1/6 atoms in the unit cell. So mark at 1, this one. So this one, you imagine this one is a hexagon. This is a hexagon shape. So each of this corner, this one, will mix with another hexagon. So you have 1/6 atom for number 1. This also same. Okay, this also same. So like you example this one, you break into 6. So in the middle one you have 6, 1/6. Okay, so this one is 1, this is 1. So those that mark as 2 contribute 1/12 atoms at the unit cell. So if you cut them, there's a top HCP and bottom HCP. One layer of this plane is already 6 already. Then another layer bottom, you get 12, 1/12. Okay, so you have number 2 here, number 2, number 2. Okay. Okay, then atom at 8 corners of the unit cell collectively contribute 4. We have 4, number 1. So number 1 is 1/6. We have 4, number 2. You have 4 multiplied by 1/2. You have 1. Okay. Now number 3, number 3 is quite special. Number 3, location number 3 centered inside unit cell, but extended slightly beyond the boundary of the cell. So you cannot calculate that one, not consider as 1. So if you cut number 3, sometimes you get the molecule, sometimes you don't get the molecule. If you cut in this cube, sometimes you cut, you don't see number 3. Sometimes you see, sometimes you don't see. It depends on the orientation. Right? So total number of cell, you can say maybe number 2 at most. Because at the 8 corners, you get 1 and 1 at the center. So maximum is 2 for HCP. So it's the lowest compared to the another 2 member. BCC, you have how many? BCC, you have how many sphere? 2 sphere, right? So 2, right? So FCC you have 4. Okay. BCC 2 meh? BC 2, right? Half 1, 2. Okay. So yeah. So sometimes we call large cell. Large cells means you have 2 multiply 3 and so on. Yeah? Okay, how to get 6? One this cube, you have 2, you repeat 3 times. This one you count 2 ma. We repeat 3 times because you have this parallelogram is you have 2 sphere, repeat 1 and 2 and 3. So you have repeat 3 times, multiply 3, you get 6. So if you get a complete HCP, we call it last cell HCP, we have 6 atoms. Usually we do analysis, we do this one only. Only we calculate 1. Okay. Okay, then HCP, we use 1 ratio to describe HCP by the ratio between A and C. A is the side, C is the height. So there is a ratio there to represent the HCP for comparison. So if you have a uniform sphere, you'll get this value. C over A for HCP will be 1.633. A perfect case lah, a perfect HCP. You'll get 1.633. Okay. What is the application in final exam or test? You will be given a set of calculation. At the end, when you do your C and A ratio, you arrive at one number. For example, you calculate. You need to calculate the height of this one. So in the test, we assume you already know C over A for HCP is 1.66. Okay, A you already know, right? A you can calculate from the radius of sphere. The sphere, there are two sphere there. A is 2R. So from 2R, by this ratio, you can find the C. Yeah. So this module won't be that direct. This module always go to the question where it asks you to select material. At the end or section C of the question will always ask you, what are the most suitable material to be used? If you don't know all this value, you don't know. You cannot solve for the section C kind of question. Okay, so these are for your reference. What happens if you have changes of ABC and angle? So you only focus on the top 2, cubic and hexagon. Cubic, you have 3 types of cubic: simple cubic, BCC, FCC, and hexagonal 4. Okay, the question will be jumping between these 4 type of cube, 4 of crystal structure system: simple cubic, FCC, BCC, and HCP. The rest is outside the scope of this module. If not, then we cannot finish this module. Okay, another one is the sequence of packing. In this case, you have layer A, layer B, layer A, layer B, layer A. This is called stacking sequence. So second sequence, A like this, B like this, A, B, A, B, A, B. Yeah. Okay, example 2. Calculate the volume of the zinc crystal structure unit cell by using following data. Volume of a zinc crystal structure unit cell. He asks you this one. So by using zinc has a HCP crystal structure with the lattice constraint A and C. Just now you already know A and C equal to 1.6 something, right? 633. Sorry, CA equal to 1.633. So how you solve? So you'll be given one table like this. Of course, we will remove the caption for the table in the test. So you'll see A and C, this one sure not BCC, not so FCC, because FCC, BCC don't have the C. So this one give you the zinc. So you focus on the zinc. You have A and C value. This is lattice constant. You have the R for the molecule atomic radius. A and C, this one. So just now 1.33 is roughly there, but is for zinc a bit special. You use this value from this table. So this one deviation from ideality, this one from experiment. So copy value A for zinc 0.2665, C equal to 0.4947, radius R equal to 0.133, C over A ratio is 1.856. And you're given this one. Okay. So you draw the HCP crystal structure. You draw hexagon, then join the six corner together. You get the bottom plate. Okay. Once you draw the bottom, you can either extend up or down. It depends on your preference. In this case, expand up. You have six corner. Join the faces together. You get hexagonal prisma or HCP structure. Label A, B, C, D, E, F, G. In this sequence, A, B, C, D, E, F, G. Label C, label A. If the question asks you HCP, this will be the standard presentation diagram that we expected in your answer. Okay. Then you pull the bottom, you draw the hexagonal shape, label A, B, C, D, E, F, G. Focus on one of the triangular because you want to find the volume. So once you find the volume of this triangular, you multiply by 6, multiply by the C, you get the volume. This actually is trigonometry question. So in triangular, you know each corner is 60 degree. All side is the same. So pull out. Okay, you draw this one, then you extend to this one, then you draw this one. The side is A, height is you don't know, you label as H. The side is A, here is the same, A. So label A, and H, and draw one line perpendicular for calculation, trigonometric calculation. Okay. So this one a bit too fast. So you have, okay, this one parallelogram equal to 2 triangular, right? One parallelogram equal to 2 triangular. So you take this one, multiply 2. How you find triangular area? Half base height, half base is A, H is height. Okay. How to find height in the term of A? Because we don't want H volume, H parameter. We synchronize the presentation. Right? To remove H, we substitute H in term of A. So H equal to sine 60, A, right? Sine this hypotenuse and side is the sine. Substitute inside there. You whole equation is in terms of A. Why we want to A? Because the question give you A. Right? Substitute the A value here, you get the area of this cube or this parallelogram. Right? So once you have this parallelogram, you multiply by the height of this HCP, means you have one cube, the highlighted both black color. Once you find that one, you will get 0.03 something nanometer cube in the nano, 10 power 9. Okay. So once you have that, the total volume of large cell means you multiply 3, because this single cell, you multiply 3, this value multiply 3, you get the answer. Yeah. So this question asks you about zinc. This question can extend to any member in this diagram. This question can extend to other member. By reverse, this question asks you either missing value of A or missing of C. Okay, so if the question asks you C, I will remove C value in the table. You have this one and this one. And normally, if this one not relevant to C over A, I'll remove this one also. So you're seeing a few relevant row and column. Yeah, so try to see whether you know how to solve when you reverse the question. Okay. So far okay, yeah? So far is okay. Only I think need to recall is the triangular equation, and then two triangular form parallelogram. I think it's wrong. Answer is wrong. Answer previously is this one, not 3 multiplied on typo error. Okay. Next, we go into position and direction of the mod or atoms inside there. Okay, so how do we give direction of position? We start with the coordinate system. Coordinate system or rectangular coordinate. So here, if you see, I think you're familiar. 0, 0, 0, 0, 1, 0, minus 1, 0, 0. This one is basically, it tells you the direction. If it's at center, x0, y0, z0. If in the x direction means you have 1, 0, 0. 1 means in that particular direction. If you go down, then you have a negative z value. If you go up, then you have positive z value. If you go to the y negative direction, you have negative y value. Same with this one. Positive y, you have 0, 1, 0. Okay. This assumes that you are moving 1 unit from the center, from the origin. Okay. So here, normally, x will be pointing outside the paper, y will be to the right of the paper, z will be going up of the paper. Okay. Okay. If you understand this one, the next is just put in the coordinate in the cubic cell. So cubic cell, this one I think in your mathematics also lah. Okay. So you have the 3 axes x, y, z, and if you draw cube, each corner of the cube, we park the cube, the lower left corner cube in the origin. We set the cube, we just push the cube, the lower left corner will be parked at the 0, 0 point. Then from there, we can write the coordinate for the rest of the coordinate. Okay. If the sphere is at the center, means half, half, half lah. Half of the sphere means half, half, half. Okay. Complete unit cell. Unit cell means one. One unit cell means one also. Length of the cube is 1. So if you move 1 to x means you get 1. For example, this cube here. X you move 1. Y you doesn't move, so you get 0. And you move Z 1 position up, so you get 1, 0, 1. Okay. Different presentation. Be careful on the presentation. You will see bracket, you will see curly later. For position, we use round bracket with the comma. Okay. First one is X, second one is Y, third one is Z, the location. Bracket, round bracket, comma, comma is a position. So these are the coordinate for BCC for 8 corners. 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, and so on. The question can just give you a position and tell me what is the volume of that, or what is the related to this atom. Let's say I give you half, half, half. Tell me what is this, the size of the atom that you can fit in, for example. That one will come into material strengthening chapter. When you mix carbon atoms or small atom inside nickel atoms, you need to calculate the space you have at this position. So I will tell you in the question, identify the maximum sphere radius that can fit at the location half comma, half comma, half comma. Means I ask you to find the sphere that can fit inside the cube. This is the application when it comes to question. So center is half, half, half. Okay. Next, just now is position. Now we go into direction. It's like a vector, like what you learn in your statics. So you need to pinpoint where do you looking at, or when you insert a cell, you need to insert a sphere in the material strengthening. You need to tell how you fit the metals, all right? So for example, in this case, direction, change shape already, presentation, from a round bracket to bracket to a cornered bracket, and there's no comma inside the presentation. Don't put comma. Comma means direction, position. Direction, same X, Y, Z. For example, this blue color, from O to X, you write bracket 1, 0, 0. Means you move in X direction, and no moving in Y, no moving in Z. Okay, it's like a vector. It's like a vector that you learn. So this one, from O to S, is actually you move X, then move to Y. Do not move Z, right? So you put bracket 1, 1, 0 to represent the diagonal arrow OS. Okay, so this one you should be able to see that. If you from O to corner T, OT will be 1, 1, 1. Because you move X, move Y, move Z. Okay, it's a vector actually, right? Now, for example, this one, you only move half to the half of this one. So initially, how you arrive at this number? In direction, there is no fraction number. You need to give full number for direction. There's no half, there's no 1/4, You only need to give full. So you need to tell how you get this one. You need to do some conversion. How you do conversion? So you write 2x is half, not half. 2x is 2x is half. 2y is half. Sorry, 2x is half. 2y is half. Let me see, huh? So this one is, this is half. Z0. X you assume as 1 in this case. In this case, if you do not number anything, you assume as 1. So 1 half 0. Initially, you have number 1 half 0. You cannot get the fraction number inside the bracket. You need to get full number. So you completing the full number, you multiply the all numbers by 2. Okay, so you will get 1 half 0 initially. This multiply 2 to cancel the fraction. So 1 multiply 2, you get 2. Half multiplying by 2, you get 1. You get 2, 1, 0. Basically, if you expand this cube, means x move 2, then y move 1, and z do not move. Same direction. Same direction if you extend this one. You extend this one. Corner to corner, you need 2 cube to complete this vector. Same with this one. Again, in the direction, if you want to represent negative, you put in a hyphen on top of the numbers. If it's negative, it's a bit different from the coordinate. Coordinate can be negative. Coordinate can put negative one. Okay. So this one, -1, -1, 0, because it's moved to x, move inside. It moved inside from here. O to y-axis, -1, -1, 0. So -1, -1, 0. Presentation is above, negative above the numbers. And the origin change. The origin change from here to here. So it depends where is the origin. It's important you say where is the origin for the direction. Okay. Okay, the rest you read. These just tell you not to confuse between the position and the direction. Round bracket and the sphere bracket. The rest you read now. Position. Okay, so this is what I explained just now, how you convert the fraction into full number. Okay, so coordinate, you can have negative inside bracket, but for direction, you need to put negative on top of the numbers without the commas also. Angle. This one you learn in your statics. Cos, sine, theta, or alpha, beta, gamma, same. Dot products that you just learn in your statics. A dot B equal to AB cos theta. All right, those taking statics, we just completed this equation. So A dot B equal to AB cos theta. A equal to AXI, AJ, AK, B equal to BX, BY, BK. Okay, so those in the statics class, you're familiar with this one. So A dot B equal to this one. We already proved this one in statics. Then you cos equal to this one, what you learn in your statics. Okay, then we'll represent the direction by using U, V, and W, like X, Y, and Z. So this one is to set the question so that when we ask you to put your answer in U, V, W, ask you to put the numbers, find the numbers of U, V, and W. And this one you see bracket, right? Bracket is mean direction. Bracket means direction. U means X direction. V means Y direction. W means Z direction. Okay. So you have all this direction, bracket, 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 bracket. Or they have 1, 1, 1, minus, minus 1, minus 1. They are all put in one family, which means all these members, they're moving in one steps or one unit. So if you see this arrow bracket, it means family. So if give you family 1, 0, 0, it means your answer can be any one of the 6 answer. Meaning your answer, inside your answer should be have 1 inside your answer. It can be moved in X, it can move in Y, it can move in Z, it can move in the negative direction, but is within family of 1, 0, 0. Why this one can be 0? Because based on your orientation. You can look from the top, you can look from the side, you can look from the bottom. But each one of it is the same, like looking at a vector. Let's say this vector is 1. So you look at the side, look at the top, look at bottom, also moving in one thing, only based on what you look, you have negative value. Right? So nothing complex, it's called family. Okay, exercise. See if you understand. Determine the direction indexes of cubic direction shown in the figure. What is the direction? Origin is here. Are you able to calculate the number? What is the direction? X move how many? What's how many steps from X to the this 1/3 position? How many steps you move? Try to write something, then you check your answer correct or not. You know how to read vector, right? Yeah. Tail is here. You're actually reading the vector. You are telling me tail to head, what is the direction? We haven't come to the references from one coordinate. We are now looking at the vector first. It tells you the direction index for the blue color arrow. Means you tell me what is the direction of the vector. For X, how you find the X magnitude that you move from half to one quarter, or one third. How many you move? Huh? How many you move for the X? If you view from the top, How many you move? If you don't know, you expand the denominator. What is the common denominator? 6, right? This one multiply 3, you get 3 over 6. This one, 2 over 6. So from 3 over 6, move to 2 over 6. How many move you move? X equal? How many? How many? 1 meh? 1? No, not 1 lah. 2 over 6 minus 3 over 6. And minus starting position, right? So I get minus 1 over 6. Then y. Y in this case, how many? You move from here to here. This is your y. Y is 1. Okay, y is 1. Z. Hey, wait. Is it Z? Sorry. No, actually, I'm give you the wrong answer. X actually moving in 1 is only the Z position. I give you the wrong answer just now. X is 1, correct? X is 1 because the blue color actually moving Z direction. Correct? 1 over R, correct? Can, right? It's actually moving from X to X. This is 1, and it's actually changing the Z direction, the Z location, from 1 over 2 to 1 over 3. So let me redraw the diagram. If you look at the Z, it's half to 1 over 3 here. So it's actually moved from 3 over 6, move down to 2 over 6. Is Z direction, sorry. Just now the one I write on the whiteboard is wrong already. It's not X, it's Z direction. Okay. So the rest you read. Okay. Okay, so this is a bit lengthy steps lah. The one I show you just now is a bit quick one. So this, they move the whole origin to the corner here. It means they shift the whole thing up. Actually, don't need lah. Actually, don't need. So you move half a bit. So this one you move up. So you only the arrow pointing from here to here. Actually, it's the same. Right. So here is 1 over 6. It's actually the same like what we did on the whiteboard. It is just it move the arrow to the new just to recalibrate the position. Okay, it's the same because vector is more about direction. So this direction and this direction is the same. The actually red color arrow and the blue color arrow is the same. Okay, so the position. This is what our draft. In X, it moved 1. It moved reverse back. It moved to the back of the X. Right. This is the X is moved. So it moved back minus 1. Then Y, it moved to the front. Y, it moved to here. So it's 1. Z, it moved down 1 over 6. So again, for direction, we don't have comma, we don't have fraction number, we don't use round bracket. So change the round bracket into corner bracket. Then multiply 6 become full number. So minus 6, 6 and 1, minus 1. So remember, negative is above that one. Yeah. This is your O origin. Here to here, 1 over 3. So total 1, right? So the distance here to here is 1 over 3, 2 over 3. Can you see? This one is 1 over 3. So this is 1. So the balance is 2 over 3. Here to here is 2 over 3. Here to here is 1. Huh? Okay. But this is just a long way, a very long way, but you can do the one that we did on the whiteboard. So just a note there. Okay, we go for another 20 minutes, then 25 minutes, then we call it a day. We end a bit early. Yeah. Ah.
Like a specific value or
Oh, no. We see it as from here, where we move from here to here. We actually move back, right? Oh. Okay, so every cube that we use for calculation, 1 cube is 1. Standard means every time you draw a cube, the length is 1. Means 1, 1, 1. If you draw direction, we'll see as 1, 1, and 1. If the question didn't write anything on the line, means it's 1. The length of the cube is 1. Because we are looking at unit cell. Okay. Now, again, this is a coordinate calculation. There's a formula to convert position into line. Go and Google and find. There's one chapter in mathematics. If you're given position x, y, z, 2 point, you can convert 2 point into 1 line equation. There's one chapter. Okay, you're given position 1, 2, position 2. So you have x, y, z to x, y, z, x1, y1, z1 to x1, x2, y2, z2. You can convert this information by one formula into y equal to mx plus c. There's one chapter in Cartesian coordinate chapter in mathematics. XY is 2D. This one 3D. Mathematics, you have, this one you have XY. If you have FYZ, you have a vector system. You arrive at one vector, for example, you arrive at one equation with this in, let's say direction. Direction equal something I, something J, something K. Okay, and okay, you can find the direction by giving this position x, y, z. Okay, x and y, yes, you can find x and y, Cartesian, y equal to ms plus c. But in 3D, you are using vector presentation. Okay, vector presentation. Okay, how you do if you're given these two value, quarter, 3 quarter 4, 0 quarter, and 1 over 4, 1 over 2, 1 over 2. You are given these two coordinate. So scratch these two coordinates in a cube, right? So build a cube, then put inside these two equations, these two coordinates. Assuming you're having a perfect cube, one side 1, 1, 1, and put in the coordinate. Okay, you draw a cube, something like this. Draw a cube 1, 1, 1. Then you should be able to pinpoint where is this 3/4 means you move, this is 1. So quarter 4 is here, this length. So this is so quarter 4 you place out here. Y0, Z, you move up quarter 4. So you draw one line, quarter 4 here. So this is the mark for the first one. Okay. Then you apply the same for the second one. X, you move quarter 4. So you put half, then another half, you draw one line. Okay. Then Y is half, so it's half here, you draw one line. So there's an intersection there already. So half. Z is half, so half here. So you draw one line. You will intersect of this one. So you put there. For the sketch line, it's important. It's important to tell how you get the position. So all these are 1. All these sides are 1. So for 3/4, 0, 1/4, remember to sketch. So this is quarter. So this is quarter. So you label. This is origin, 0, 0, 0, 0. So here to here is 3/4. Y0 is over here. Quarter 4, you label this one. Then use your ruler. This is quarter 4. Draw a line up, parallel to this line. This is the position, the first position. Draw the same for the second one. Quarter 4 is over here. So this is quarter 4. Then half of a Y. This is half. Draw one line up. So quarter, half here. So this is half. You want to draw a direction indexes between position 3/4 to 1/4. So this is the vector. You need to find the differences between the x and x, y and y, z and z. So x2 minus x1, you get one number. Y2 minus y1, you get one number. Z2 minus z1, you get one number. Just remember whether it's moving forward or moving backward. Okay, for example, x is x2 minus x1, 1/4 minus 3/4. You get minus 2/4, which is half. Right? Y2 minus y1, half minus 0, you get half. Z2, 1/2 minus 1/4, basically is over 4 minus 1/4, you still get 1/4. Change the bracket, round one to the right corner one. Okay, so this is the steps. You draw the cube, draw the blue arrow, then find the changes of x, changes of y, put into the bracket form. Okay, so this is not the correct one because we don't want to see the fraction. So take the highest fraction, change this one to 4, this one to 4, this one to 4. Then multiply 4. Then flip the negative, put at the top. You arrive at this answer. Okay, so this is the answer we looking at. Bracket -2 with the negative on the top, 2, 1. Okay, vector always you calculate from the tail to the head, arrowhead. Okay, we still haven't go into the references relevant from one position yet. We are now looking at the vector position. Okay. Okay. So next we try to write a more professional way. We call it Mueller index. Right? Mueller index or Mueller notation system. Like what you learned just now, you just put in the form. So these are the procedure like what I already focused on. Miller indexes is HKL. This one for Miller indexes HKL. Okay, for example, this coordinate bracket, right? Sorry, this is for plane. Plane. Now we look into plane. Just now we have position, direction, family. Now we look into plane. Plane means a piece of A4 paper. Plane is bracket without the comma. Bracket without the comma. For example, A100 means the plane is perpendicular to the x, means you move x in one direction. Okay, you imagine the plane as A4 paper. Okay, you start from 0. Start from here. Then, if you have number 1, you move the whole A4 paper 1 steps. Okay, you move from the origin, you move 1 step x. You get this presentation. If you are given Miller number 110, it means you move 1 step out, then tilted y. You move y 1 steps. Origin like this one. Okay, then you move to the front already, then 1 is y. 1 also 1. Okay, then the slanted one is 111. Okay, 111. Or more easier to remember, you just remember the x coordinate. Then if 0 means you pull the A4 paper to the location of x. If you have one number 11 like that, you pull your x code, your A4 paper to x1, y1, then z infinity. Okay, 0 means infinity. Then you have 111 means all the corners slanted at certain angle. X1, Y1, Z1, then you draw the plane. This is called Miller numbers. So this 111, this is HKL. HKL. Without comma. If you put comma, it becomes position already. Okay, the rest is just read if you understand. Okay, next is more add-on, more revision. What happens if you're given a 3 coordinate like that? You are given this coordinate, this length and this length. Are you able to find bracket 632? Okay, so you just need to find what is the x location from O to this position, 1/3. Y is what? Y is 2/3. What about Z? Z is 1. Z is 1. If you do not give any coordinate, it means 1. Okay, then we don't like the fraction number. Find the common denominator, multiply. You will get 6, 3, and 2. Okay, 1/3, 2/3, 1. We don't like fraction, multiply the whole thing by 3, you get 1, 6, 1. Sorry, 1, 6, 3. You wanted 3? 3 over 2. Sorry, I read the 1 over 3, 2 over 3, then this one is 3. Then there's a step there. So in intercept 1 over 3, 2 over 3, 1. Before you do these steps, there is a cheat steps. Mathematics, you flip reciprocal. You flip the number. Means 1 over 3, you flip, you get 3 over 1, you get 3. You flip 2 over 3, you flip, you get 3 over 1, you flip, you still get 1. Then find the denominator. Okay, multiply 2, you get 6, 3, and 1. 6, 3, and 2. This is the Miller indexes procedure. Okay. How you do this? Why there's a reciprocal? This one on mathematics side, that is not our concern. Your concern is how you apply these steps. Okay. So to find the Miller indexes, remember to inverse the numbers. You find the coordinate first, then you flip the number, find a common denominator, make it into a full number. Can Good. All right. So the rest is same. Okay, same lah. So for if you see bracket, it means on the plane 1, 1, 1 means you have 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. So this one is if you see curly bracket, it's also mean family, but this one for plane. For plane. Arrow bracket for family, for direction. So don't confuse between the curly and the arrowhead. Yeah.
Let's say the coordinates of a point, but using the normal style, which is like the cube. Will it be different from having the same coordinates for the same points, but on the Miller plane?
That one have two part the question. One, you need to find the direction. One, you need to find the Miller indexes. There are two parts. Either you are finding direction or you're finding plane. These two questions is a separate question. Okay, plane. Plane is like a piece of A4 paper. Okay, so if you are finding Miller indexes, then the vector can be moving along this plane. Let's say you want to control the movement along this plane only. Then let's say your strengthening mechanism, you insert from this direction only. You can only do either you remove particles or remove sphere from this plane only. Then you need to fix these Miller indexes in the process. This is the purpose of application. So the vector and the Miller index is a two different dimension. You can put your vector on top of the Miller, or your vector can go outside the Miller plane. So it's a different two things. Don't confuse between these two. Okay. These are the other things that you can work on when you do on the material engineering. You want to slice the material at a certain, like for example, those diamond cutter, they cut diamond at a certain angle. They do this one. In the procedure, they'll see, you need to cut the angle using Miller indexes, like how you cut. These are the things, how you cut the things, because it's a laser cutter, it's in the plane. When you shoot laser cutter, is in the like a A4 paper. This is how you cut the thing. You spray the laser like this one or a certain angle. This is how you apply the Miller index. Okay. So equivalent, for example, 110, it can be like this. 001, it can be like stacking. 110, it can be like this. It can be stacking. So you can duplicate the plane. Okay, it just tell you the direction. What is the orientation of the plane? You can duplicate it at a certain coordinate. This is called Miller lah. Okay. Combine what you learned in HTTP or the HTTP BCC crystal structure. You combine with this chapter. It depends how you cut. So for example, the B you see here is A and 1 over A here. Right. So this one, so this one is a cube of A and 1 over A. How to get this one? How to get 1 over A? This one is A. So 1 over A is AA is like that. So this is square root of 2A. Make sense? Sound right? A 2A square. Correct. Okay, so it depends on the length of this one. It depends on how you cut it, right? But anyway, important is you understand the line and the plane. So direction again is bracket minus 1 1 1 minus 1 minus 1, and the plane is 110 plane. 110 plane means it's slanted 45 and you cut the cake, right? 111, you on the plane you cut in this direction. If you're having 111, so your origin is like that, you cut like that, is what you cut. If you're cutting at 110, you slice the object like that. Then you are seeing, if this one is BCC, what you see is here like that. Okay. So yeah. So it's like X-ray lah, like X-ray. What position you want to see? Dissecting the things. This one you can practice if you want, right? So draw the plane of 101. Right, 101 means you move X one steps. Y it doesn't move. So Y doesn't move. Z you move 1, right? So 101, you can do the indexes, right? So how you arrive at 101, you reverse the steps, because before you arrive at this one, you do reciprocal, right? You reverse the things. 1 over 1, you still get 1. 1 over 0 is infinity. 1 over 1 is 1, so you get 1 infinity 1. Okay, so you go to the Z, so you move 1 X. Z is Y is infinity. Y is infinity. Then Z you move 1 up, so it's a slanted this plane. It's called 101. Okay, so if you are given this Miller index 101, the step is you do the reciprocal first. You inverse the numbers to find the location. For example, 101, you get 1 infinity 1. So you draw the plane by 1. Y is infinity, so you expand the Y, and then you need to move Z 1 steps. Okay, so it's presented like this. You repeat the rest for your revision. Same, 1 minus 1 0, you reverse 1. Inverse 1 is 1, minus 1 minus 1, 0 is infinity. So you move 1, Y minus another side, Z infinity. So it will be like this. You move X, move Y, then Z infinity. Yeah, it's like you're starting from 0, then you move X, all right, move X like this, move X, then move Y, then Z infinity. Okay. So this is just to tell you when you have negative, it means you move to the left-hand side of the axis. Do the same, 2, 2, 0, inverse the things, reciprocal, you get 1 over 2. Inverse 2, you get 1 over 2. Inverse 1, you get 1. Okay, so you'll pass through half, half, and 1. You draw the plane. So you put in x is half, y is half, z is 1. So you pin the 3 point, half, half, and 1. You draw connecting the plane. You get the plane things. Okay. D, draw 110 plane in BCC atomic structure shell. List position of coordinate of the atoms whose centered are intersect with this plane. So this one combined with what you learned in crystal structure and this Miller plane structure. So what you do, you draw the crystals, you draw the unit cell first. You draw the 111, the cube first. Then you inverse this one. Inverse this one, you still get 1. Inverse this one, you still get 1. Then this one, 0 means infinity. Okay, then you connect the dot, put in as a A4 paper, a plane. Then only you put inside the presentation of BCC atom. Okay, so this one you inverse lah. Inverse. So the blue color plane is 110. Okay, 110. X1, Y1, Z infinity. So you have 2 dot. You combine these 2 dot, then you expand out. You get a 45-degree chop like that. Okay. Then they ask you list the position coordinate of atoms whose centered are intersect by this plane. So if you cut BCC plane by this plane, you cut laser cut. The atoms that touch by the cutting plane is what? This one, this one, this one, this one, and this one. So what are the coordinate? Right? So these are the coordinate. You have this one. This one is 1, 0, 1. This one is 0, 1, 1. Of course, with comma, with comma. This one is what? 1, 0, 0. This one, 0, 1, 0. Center, half, half, half. Means half lah, half, half, half lah. Center ma, half, half, half. Okay. So these are the kind of question we're going to come out in your test 1. Final exam maybe not, because this is very simple exercise. So we try to help you in test 1 and test 2. So usually test 1, test 2, they are quite easy lah. If you understand this one. So of course, BCC already give you already. What happened if the question change to 0, 1, 1? Are you able to tell the intersect of coordinate? You should able to do. So or it changed to 1, 1, 1. What are the coordinate of the cell that intersect with this plane? You should able to do. Yeah. The rest is just cubic system by calculating the D of HKL. HKL is the index, Miller index, this one. For example, plane 111. 111 means the angle of the plane. So you can change the plane. You can move the plane according to the coordinate. Like you're moving X-ray scan, the MRI. You do brain scan, right? You have an X-ray of 111. So you move the distance of the scanning distance. So this one is a distance between the 2 plane. you label as D110. So this is a D, this is a D. So this is how we control in the X-ray machine, especially MRI. Like how many dissect you want to do, what kind of picture you want to do in this distance and this distance. Then they combine, you get a 3D model. Okay. Distance between two planes. This one okay, this one is just illustration. Okay, this one is a trigonometry. How to find distance between HL and K, for example. You take A and HLK. Square is distance is here. So the so you take A divided by magnitude of HK and L. This is just a formula lah. You just memorize, and if you see the question give you HLK, you just substitute accordingly lah. Okay, example 6. I think this one will be the last example for today. So determine the Miller indexes of the cubic crystallographic plane shown in the figure. So are you able to tell how you tilted the plane? First, write the coordinate first, then you inverse the numbers. So what are the x number you have? 3/4, y 0. Sorry, y is 1/3, z is infinity. Z is infinity. So you reverse the numbers, you'll get something infinity lah. So it depends lah. So this one is slanted a little bit. It's slanted a little bit like that. So sometimes the question you can do your way. So this one you can move this plane to origin if you want, right? So this one is move a little bit. So it's either move to this one or move to here. This question is move this plane to here, just to synchronize. Okay. So from here, you move the plane to the side. So you're finding the distance over here. You take 3/2 minus 1/4. This is the distance, 3/2. You move 1/4 already. So 3/2 minus 1/4, this is the distance you want to find. Okay, this is the distance you want to find. Okay, so you have 1 minus 5.2 and infinity. Okay. You reverse the thing, 1 become 1. 5/12 become 12/5. Then infinity becomes 0. Okay, then put this presentation into a good one. We don't want to have a fraction value. So multiply by 5, you get 5 minus above the numbers and 0. So this is a Miller indexes. This is H, L, and K. H, L, and K. Right? So if we given the A value of the things, you can apply this equation to find the distance between the two planes. If you're given A lattice constant, so lattice constant, you can find whether it's BCC, FCC. BCC, FCC, you know already. A equal to what R? Is different. So it's based on BCC, FCC. Example 7, your homework, go and see. All right. There is a YouTube video I attach here. Go and view. Let's see. Okay. So this video, I'm not sure whether PDF you're able to click, but you can go to video, go to YouTube, go and finding a 3D line through 2 points. Go and watch. If you already forget how to find the 3D line from 2 coordinate, go and view this video. Okay, we already assume you know. So go and see this one as your homework.
We want.
Okay, at the end, you get one number. Okay, go and see the video. Example 8, also your homework. Go and see, just substitute value. We will continue next lecture 3.7. Okay, so you have a few homework. 2 homework, go home and read the tutorial question.